Let's consider controlled NOT operation. Controlled NOT operation flips the target bit if the control bit is equal to 1. In the classical computation, we are used to the fact that if we apply the CNOT operation, the state of the controlled bit never changes. However, in quantum computation, it's not always the case, and under some conditions, controlled operations can act the other way around. They will change the state of the control qubit, and the state of the target qubit will remain unchanged. This happens due to the so-called phase kickback phenomenon. In the most general case, the phase kickback occurs when we apply an arbitrary unitary operator in a controlled way to the system, where the state vector of the target qubit is an eigenvector of U. This operation will not change the state of the target bit, but it will induce a phase shift in a state of the control qubit. To be able to measure this effect, we must prepare the control qubit in a superposition state. Let's consider two-qubit system. We prepare the control qubit in a superposition state by applying a Hadamard gate. And the state vector of the target qubit is equal to an eigenvector of U. Then, we apply a controlled unitary operation to this system. Since we do it in a controlled manner, the unitary operator acts on a target qubit if only the controlled qubit is equal to 1. Since the state of the target qubit is an eigenstate of U, the action of U creates a phase factor that is equal to the corresponding eigenvalue. However, if we rewrite the state of the system as two separate qubits, it turns out that the state of the target qubit did not change, but the state 1 of the control qubit acquired a relative phase with respect to state 0. Thus, the phase factor, which should have been applied to the target qubit, is kicked back to the control qubit. The phase kickback is equivalent to the application of phase operator, which is rotation around the z-axis, on the control qubit, where the rotation angle is set by an eigenvalue of the applied unitary operator. Let's look at a few special cases. First example demonstrates the phase kickback when applying conditional NOT operation. In this case, we apply the X operator to the target qubit if the control qubit is equal to 1. For convenience, we calculate the eigenstates and eigenvectors of X. Solving a simple equation, we find that the X operator has two eigenvalues which are equal to +1 and -1. Then, we search the eigenvectors in a form of a linear combination of 0 and 1. And solving another simple equation, we find that the corresponding eigenvectors are plus and minus states. Now we take two qubits and prepare the first qubit in a superposition state and the second qubit in the first eigenvector of X. Now, two qubits are in the same plus states. Then we apply the CNOT operator using matrix representation. The state of the system did not change, and it's not strange, because an eigenvalue of the plus state is equal to 1, and the phase operation on the control qubit is equivalent to identity operation. Then we send to the target qubit the second eigenvalue of the X operator, which is minus state. CNOT operation is applied to plus-minus state, and in this case, the state of the target qubit did not change, but the control qubit flipped the sign. The eigenvalue of minus state is -1, and the application of CNOT to plus-minus state is equivalent to the application of Z operator to the control qubit. The second example demonstrates the phase kickback using conditional phase operation. In this case, we apply the phase operator to the target qubit if the control qubit is equal to 1. We again calculate the eigenstates and eigenvectors. Solving a simple equation, we find that the phase operator has two eigenvalues, which are equal to 1 and e to the power of I phi. Then we search the eigenvectors in a form of a linear combination of 0 and 1. And solving another simple equation, we find that the corresponding eigenvectors are 0 and 1 states. Now, we take two qubits and prepare the first qubit in a superposition state and the second qubit in the first eigenvector of phase operator, which is state 0. Then we apply the CPhase to the +0 state. The state of the system did not change because the eigenvalue of the 0 state is equal to 1, and the phase operation on the control qubit is equivalent to identity operation. Then we send to the target qubit the second eigenvalue of the phase operator, which is state 1. CPhase operation is applied to +1 state, which results in a phase accumulation between 0 and 1 states of the control qubit. The state of the target qubit remained unchanged. The eigenvalue of one state is e to the power of I phi, and the application of CPhase to +1 state is equivalent to the application of phase operator to the control qubit. Thus, there are several conditions which should be fulfilled to cause a phase kickback from the target qubit to the control qubit. First, the unitary operator must be applied in a controlled way. Otherwise, the application of U just creates a global phase which cannot be read out. Then, the state of the target qubit must be an eigenstate of U. And to be able to observe this effect, the control qubit must be in some superposition state. So, what is important to know about the phase kickback? Phase kickback affects the state of the control qubit, and the state of the target qubit remains unchanged. It means that the single qubit can read out the action of an arbitrary large unitary. Therefore, circuits realizing the phase kickback are important building blocks of various quantum algorithms.